I will begin. Heavenly Father, we thank you for this day. Just pray you help us use this time wisely to prepare for the test tomorrow, and just to, whatever we do, Lord, we do it for your glory. In your name I pray, Lord Jesus. Amen. All right, where are we? So do you guys have any questions? Should we look at the start of the math battle, probably? That'd probably be a good idea. So find the points on the surface closest to the origin. So here's a sad picture of the surface, which is not really accurate, but I always make some stupid picture just to help me kind of start my thinking. So the point on the surface is x, y, z. The distance from the origin is square root of x squared plus y squared plus z squared, but I don't like square roots, and we might just as well minimize the squared distance, because the squared distance is smallest where the distance is smallest, right? Which we could prove mathematically if you'd like. But I'll go on. So we have that objective function, x squared plus y squared plus z squared, and we have the constraint xy minus z squared equals to minus 1, or if you like, z squared minus xy equals to 1, whatever floats your boat. Anyway, that's the constraint, that's the objective. So I'll use the Lagrange multiplier technique, which gives me 2x, 2y, 2z equal to lambda times y, comma x, comma minus 2z. That gives me these three equations, and you may have solved them different, but here's how I thought about it. I was like, oh, so the third equation tells me that twice lambda plus 1 times z is equal to 0. So that gives me two options. Either z is 0 or lambda is minus 1, right? So that's one thing. I'll come back to that. I actually wrote that in later. I know it's hard to tell, but I will come back to that start equation. Now, just going from here, if I solve for lambda, I get lambda is what? It's 2x over y. And for this one, lambda is 2y over x. Of course, when I write that, I'm assuming that both x and y are non-zero, right? But anyway, given that, that gives us that 2x squared equals to 2y squared, which then implies that x is plus or minus y. But on the other hand, from star, I've either got lambda's minus 1, and if lambda is minus 1, then this tells me that this first equation tells me that 2x is minus y, right? And then the second equation tells me that 2y is minus x, which tells me that x is equal to minus 2y, which then implies that y is equal to 0 and x is equal to 0. But again, I really can't have that from this case, so I'm not sure. Let me think about that. I mean, this algebra definitely doesn't allow x and y be 0, but I guess once I get x equals 0 and y equals 0, I can go back before I made that division and think about whether or not it makes sense. I mean, I think it does make sense. If x and y are both 0, this equation checks, that equation checks, and if lambda is equal to minus 1, this equation checks. So, I mean, again, this conclusion escapes my derivation, but if you go back and think through it, x and y both being 0 does give us a solution to this, paired with lambda equal to minus 1. And in the case that x and y are both 0, that means that z squared is equal to minus z squared is minus 1, so z is plus or minus 1. So however you do the algebra, you should discover 0, 0, plus or minus 1 are 2 points of interest. On the other hand, if I look at the case that, let's see here. What am I doing here? So I was chasing it a different direction. If I start with plus or minus y, I get 2x is lambda times plus or minus x, which gives me that lambda is plus or minus 2, which then tells me that this is that, which suggests z is 0, which then tells me x is plus or minus 1, and then y will be plus or minus 1 as well, I think. So anyway, I found also solutions 1, minus 1, 0, and minus 1, 1, 0. I'm not entirely, I think my logic is not the crispest and most crisp in here. I like to have logic which is a little bit easier to follow. Let us agree, though, that once we find points, we should go back and check the original equations, see if they work or not, right? So these, if I go back up into here, if I have x equals to 1 and y equals to minus 1, that means that lambda is what? Must be that lambda is minus 1, right? And so then I get minus 1 is 1 times minus 1. That one checks. Okay. I have lambda is minus 1, but z being 0 makes this equation check. So I do think that both of these actually work as possible points of interest. However, when you actually plug in these points into the distance squared function, we get 1 from this one and that one, and we get 2 from this and that. So square root of 2, of course, is a greater distance than 1. So apparently this and that are the closest points on the surface. So at that point, because I knew my algebra was a little bit shaky, you might have better algebra, right? And but I decided I'd try to think about what this thing actually looks like. So if I solve this for z, I'd have z is plus or minus the square root of 1 plus xy, right? And where is that going to appear? Well, it's going to appear in the region where 1 plus xy is non-negative. Where is 1 plus xy non-negative? Well, that's where xy is greater than or equal to minus 1. So this, if x is positive, I get y is greater than or equal to minus 1 over x. So x positive, y is equal to greater than or equal to minus 1 over x. That's this region in here. On the other hand, if x is negative, when I divide by x, I reverse the inequality, and I get, hey, oh man, come on. Well, reversing the inequality doesn't make the minus go away. Doofus. Oh, stink. Well, I'm glad we talked about this. So I should have, can you turn on the light for me? Thank you. This middle case should have been y is less than or equal to minus 1 over x for x less than 0, right? So drawing the picture again, I still think this is reasonable. What's y equals to minus 1 over x? That's this curve right here, all right? Less than or equal to minus 1 over x, that's down here. Right? And then what's x equal to 0? Is x equal to 0 a solution here? You know, if you have x equal to 0, y can be whatever it wants, right? And what's z equal to? Z squared is 1, right? So z is plus or minus 1, the solution set. So if you think about that, that's definitely in the domain. In fact, there's two different strips. There's a z equals 1 strip, and there's a z equals minus 1 strip, both in the surface. There's apparently two parts to it. I'm not sure what that looks like exactly, but it'd probably be instructive to actually look at this thing in Mathematica or something, right? But anyway, it made sense to me, the answer, though, because basically what I'm finding is that along the y-axis, right, the value of the graph is either at z equals 1 or z equals minus 1. And so if you think about it, I think that it makes sense that that was the closest point, either above or below. Any other point on this place where z is equal to 1 is going to be further away than 0, 0, 1 or 0, 0, minus 1. And any other point is going to have a z value which is larger than, in magnitude, 1, right? And you can't, so you always have a z value, a distance in the z direction which is larger than 1, and then whatever else you have in terms of the x and y direction. So it makes sense to me that these 2 points are the closest points, despite my algebra. All right, anyway. Problem 2, hopefully is a little bit more straightforward. The stupid algebraic solution is just to recognize after you complete the square, this is just 2 plus the distance squared from 1, 0 to the point xy. Like this is the distance from 1, 0 to xy squared, right? So if you pick the point 1, 0, which is about right here, and you look at circles of equal distance from that central point, and you look at those circles, the circle which is largest and hits something in the triangle is the circle which intersects R. So it makes sense that R is going to be the maximal. It's going to be where the objective function, attains its maximum, just on the basis of geometry alone. I will be careful on the test to add the sentence which says use calculus. Okay. It's usually the case, though, it's friendliest for me to ask a question which has a geometric solution, because these questions tend to be more manageable algebraically than if I just pick one which forbids an algebraic solution, you know? Just saying. Anyway, so here's the algorithm. What you want to do is you want to look at first of all, you search the interior of the triangle for critical points, right? So look for where the gradient of the objective function 0. In this case, we just get 1, 0 is the only critical point. The value of the function at 1, 0 is 2. Okay, so great. Save that for later. And now I need to analyze the boundary of t, which has 3 pieces. Chunk, 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 right? And so I just restrict the function on each one of those line segments. I've got to parameterize the line segment, right? And then evaluate the function at that parameterization. That gives me a function just of time. You know, resist the temptation to multiply stuff out. Chain rule, much easier. So the chain rule gives me this, if that's 0 at 0.4. And so here's my 3 points of interest by the closed set test on G1. I get 6, 3.8, and 11. On part 2, again, parameterize the line segment from R to Q by this and that. I plug it into the function. I differentiate using the chain rule. I get that 24 equals to 0, which is hard to solve. So there is no interior critical point on this leg of the triangle. If I actually, what would happen? So you guys did this, some of you, right? What happened when you actually squared these out? Did you guys get this as well, or is this a mistake on my part? I mean, I do make mistakes. What's that? You didn't get that. Anybody else get that? No other team got this. Just me. Well, huh. Wonder where my mistake is. Is it the parameterization? I'm trying to go from 0, 4 to 4, 0. I think I do that. Well, I don't know, guys.
Where does 14 minus 1 squared come from?
The negative 1.
That's x minus 1 squared, the formula for f.
Oh.
But maybe that's a good question. X minus 1 quantity squared, that means I'm adding 1. So I take away 1 from that, which gives me the 2. And the y squared is just still there, so. So then I was putting x equals to 4t, and so I got 4t minus 1 squared there, and y was equal to 4 minus 4t. That's why I had the 4 minus 4t squared there, and I evaluate 4 minus.
Add a negative 1, should you be adding back to the top page, sorry. If you add, or have a negative 1 in the x minus 1 squared, shouldn't you be adding 1 to the 3 and make that 4?
No, because when I square it, I get minus 1 times minus 1, which is 1. So grouping it as x minus 1 squared is effectively like adding 1 to the expressions. I have to take 1 away to be fair, yeah. Yeah, I don't think that's where my mistake is, if there is a mistake here. Maybe you guys are all wrong. Yeah, let's be optimistic. You're all wrong. All the teams are all wrong. I alone am correct. No, that seems unlikely. Huh. Is it just here? I mean, 32t, negative plus minus 0.
You're taking the derivative from the line above to the line below, right?
Yeah.
Shouldn't there be 2 times 4t minus 1?
Yeah, but that times 4, because of the chain rule, gives me 8. And then over here, I get, oh, here it is. Here it is, guys, right here. Right here. Why is this to that wrong? Should be negative, right? Because the chain rule says so I get twice twice this thing times the derivative of the inside function. The derivative of the inside function doesn't just give me 4, it gives me minus 4. So I should have minus 8 here. That's my mistake. If I put that minus 8 there, then we get 64t equals to 24, which gives me another middle point to check. Yeah. So you guys got a middle point on all 3 legs. Okay. Good. So sorry about that. There's obviously a mistake right there. But on the other hand, we noticed that f of r is 18 and f of q is 11. Finally, the third leg gives me another middle point at t equals to the third for me. And I get 6, 3, and 18. So anyway, long story short, the maximum is attained at r. At 0, 4, where I get a value of the objective function of 18. You guys get that? Everyone, I think we should all have agreed on that, even though I have a sin of omission, right? Not commission, so we should agree. Any questions? All right, well, I'm going. So problem 3, this should be pretty easy if you've understood what I've said before about this stuff. So we're given the multivariate Taylor's expansion. And so we can look at this, and there is no term with x, no term with y, no term with z, right? So we can read by inspection that the gradient at 0, 0, 0 of g is just 0, 0, 0, which tells me that indeed 0, 0, 0 is a critical point. And if you look at it, 10 is going to be a local maximum for g, because any direction I go from 0, 0, 0, I'm subtracting a sum of 3 things, right? So it's necessarily smaller as you go away from there, which means it's a maximum, because it's like going down the hill. Don't try to visualize that hill, no matter which way you go. I mean, if you imagine yourself at the top of the hill where you can go in 3 separate independent directions, then you go ahead and visualize it. But yeah, it's hard to do. Anyway, any questions about this? What if instead, just to check you guys, what if we had, instead I had 10 minus x plus y plus 3z minus 10x squared minus 11y squared plus 13z squared. In that case, if that was my g, that was my multivariate power series expanded at 0, 0, 0 for g, what would the gradient of g rather been at 0, 0, 0 in this example? Negative 1, 1, 3, right? And then you said, oh, not a critical point. Done. You don't have to analyze the critical point if it's not a critical point, right? But that said, if this was gone, right? Suppose that was gone. Then then you'd have the gradient of g would be 0, 0, 0. And you'd conclude that it was neither a max nor a min, because going in one direction increases the value, and going in different directions decreases the value. So that's what we might call a saddle point. But again, I would not encourage you to try to visualize that saddle. Okay. Problem 10, skipping ahead a bit, is very much like the ellipsoid problem that I did with you guys in class, right? So same song and dance. We make a u equals x over a substitution, a v equals y over b substitution. So in the transformed variables, it changes from the ellipse to the unit disk. And so I calculate the Jacobian, I get AB. So the infinitesimal area element in the UV coordinates is AB du dv. And so the area of E is, by the change of variables theorem, the integral over the transformed region, AB du dv, which, by the way, pull the AB out, they're constants, is this. But that integral is exactly pi, because we know the area of a unit circle is pi, right? If you don't know it, and you must insist on deriving it, great, here it is. So here's the proof that that's pi. I can change u equals to r cosine theta, v equals to r sine theta. With that change of coordinates, my Jacobian matrix works out to r. And so we got du dv is r d theta. And by the usual song and dance, the polar coordinate version of the unit disk in uv is 0 to 1 for r and 0 to 2 pi for theta. When you do the integral, of course, you get pi. So. But, for a problem which has a different starting point. Now, okay, if the problem on the test is derive the volume of a sphere, right? Or I say something like show the volume of a sphere of radius r is 4/3 pi r cubed. If your solution is the volume of a sphere is 4/3 pi r cubed. We know this. That will get you some partial credit, and also my anger, and some kind of mixture of both of those. I'm not sure exactly what's the proportion, but you know, of course, there you should actually work it out, right? But if the problem was calculate the volume of the ellipsoid, right, like we did in class, it is perfectly acceptable in that problem once you get to the integral. In that problem, we got to the integral of u squared plus v squared plus w squared less than or equal to 1 du dv dw, you know? And we pulled out the ABC in that problem, right? So in that kind of problem, it would be totally reasonable for you to say, you know what, that's the volume of a unit sphere. We know from previous work that that's 4/3 pi. I'm totally fine with that. What I'm not fine is when it's the whole problem just saying, well, that's the answer, all right? I mean, you understand the difference? So, because you already, in the problem I'm talking about, you already made a non-trivial step to realize that the given integral, right? So you actually had to do work to get to this point, right? You had to change from dx dy dz, right, over x squared over a squared plus y squared over b squared plus z squared over c squared less than or equal to 1, the ellipsoid. We did this in class, right? We found the Jacobian was ABC. And so like in this problem, yeah, fine. You don't actually have to, if you don't want to, in that particular problem, show me that that's 4/3 pi. It'd be okay to quote that result. I'd like you to know that result. I mean, I think you should know that the volume of a unit sphere is 4/3 pi. I think you should know that the volume of a unit circle, excuse me, the area of a unit circle is pi. So, just saying. Enough about that. Oh, and that's the totality of the new problems on your math battle, from my perspective. The rest of your math battle was actually an old test 3. Well, with a problem or two stripped off of it. One of the things that was missing on your math battle was this change of coordinates from, change the gradient to cylindrical coordinates problem. I think that was on your last test already, right? I think I already tested on gradient and other coordinate systems on test 2 in here. So, say hi. Maybe you'll see it again at the final. Problem 1, you can ignore it. Problem 2 would actually be reasonable for you guys, but I will go on. Problem 3 was actually on yours, right? So, what? Oh, did I have that Z on the math battle too? Oh, man, why didn't you guys ask me about that? You just ignored it?
You were going to say cross it out.
Yes, okay. Mention that to me, because while you guys have the sense to ignore it, somewhere in here, there's someone who was actually thinking about what's the Z about. Am I wrong? Okay, I have acknowledgement. See, so, those of you who have a better understanding of where you are and what you're doing, when you see typos like that, it's so important to just tell me, please, especially in the test. If somehow one of these gets past my, my checking. Anyway, that Z is not supposed to be there. All right, anyway, that said, we calculate the gradient, set it equal to 0 for critical points, factor a y out, right? Factor, I guess I can't factor anything here particularly, but the first equation either means x is a half or y is 0, right? And so if x is a half, then this gives me that y is 1/8. On the other hand, if y is 0, then the second equation tells me either x is equal to 0 or x is equal to 1. So by my count, that's 3 points. 1/2, 1/8, 0, 0, 1, 0. And then I make this like little table. And I'm using the second derivative test to check my critical points. The Hessian, which is what? fxx times fyy minus fxy squared, which in this case works out to that. Then I need to plug these points into that and see what happens. I get a half, minus 1, minus 1. So the half, I then have to check the second derivative of x. When I put y equal to 1/8 into fxx, I get 1/4. That's positive, which tells us local minimum, since d is positive. Yep.
How do
Uh-oh. I don't like your question. Yeah, it could be that I'm wrong.
Well, see, the x derivative, you have the y factor already, and so the y just goes to 1, right?
Yeah, if I take the y derivative of this, I get 2x minus 1. If I take the x derivative of that, I get 2 minus, take the x derivative of this, I get what? 2x minus 1. So either way, I get 2x minus 1, yeah?
Shouldn't you be able to look at the x squared y minus xy plus y squared and find it there too?
Yeah, but you do. This is fy, so if I take the x derivative of that, I get 2x minus 1. Yeah, it shouldn't matter which one you do, but I think I get this. It's right. But of course, so the big D, the Hessian, whatever you want to call it, being negative means we're at a saddle point. Okay. So there, that's this pretty standard test question right here, right? The main thing that'll get you guys stuck is not being able to do the algebra up here, right? So it's so important to calculate the partial derivatives carefully and to look for factoring. Remember the logic here. A critical point is where both of the components of the gradient are 0. So you have to impose both of those things being 0 to find your solutions. So if one of them factors, that's all you really need, right? Because if one of them factors, then you can divide and conquer like I did here. The fact that the first equation factored allowed me to break it into parts logically. Either that's got to be a half or that's got to be 0. If that's not a half and that's not 0, if one or the other of those possibilities isn't realized, then there is no way to make this product be 0. So logically, I either have that case or that case, and I can just chase those down from there, right? Yeah.
Why did you not have to find the second derivative, like the fxx, on the other two?
On the other two.
Like on the two at the bottom?
Oh, it doesn't matter. The second derivative test says that if the big D is negative, it's a saddle. When the big D is positive, if fxx is positive, it's minimum. If fxx is negative, it's a maximum. Just like the second derivative test from Calculus 1. So I would give you further advice about how to memorize that, but I would remind you that you have a 3x5 card. So, and they make pens with a very small font, right? I mean, like if you write with a pen like this, you can put a lot in the card, right? I'm sure you guys probably printed out on like size 6 font or something with your laser jet or whatever, right? I don't know what you got. Okay, I'll shut up. Finally, a good problem. A ninja hound is caged in a region with boundary that, and once his energy reaches a level of 5, he can change form into an eagle and escape by flying over the ellipse-shaped fence. Given that his energy level is that, is there any place or places in the cage which allow him the energy to escape? Ooh. So apparently his energy is 3 at the origin, right? So how did I treat this? I need to look for maximum energy, right? So first of all, I look for where the gradient of the energy function is 0 to find any local mins or max. And then I'm going to use the method of Lagrange multipliers to see what happens on the actual elliptical, the ellipse-shaped fence. And so first of all, only the origin, so f0, 0 is 3. That's not enough to change into an eagle, right? By the way, the assumption in here is that if he can change into an eagle at the origin, then he stays an eagle as he's flying, all right? You could have asked me about this if it had been an issue. Just saying. What's that? It's it's not like that. It's like a phase change, right? Like once, it takes a certain amount of energy to become an eagle. Once that has been, it's much less energy to continue flying as an eagle. I'm sorry, I don't know why I'm explaining the metaphysics of this fictional ninja problem, but anyway, so the gradient of f is lambda times the gradient of g, which gives me these equations, which anyway have this solution. plus or minus root 2. I should really spend more time on this algebra and make me feel better about my algebra skills as compared to the first one I did, which was, I don't think the algebra was wrong in the first problem I showed you. I just think it was not neat. This is better, I think. So what I'm saying here is a usual strategy for me, at least, is to solve for lambda. I don't care what lambda is. Lambda is just a tool to find extremal points, right? So whatever lambda is, whatever, I don't care. So, and also for this technique to work, it's got to be non-zero anyway. So solving for it kind of makes sense. I mean, it makes sense. It doesn't kind of make sense. I say kind of too much. I kind of think. Anyway, 8y squared equal to 18x squared, which gives me that. And then once I have that, I plug it back into the ellipse equation to get 18x squared is 36, which gives me, again, x is plus or minus root 2. Once I know x is plus or minus root 2, then I put it back into the ellipse equation again to find that y squared is plus or minus 3 over root 2. So that gives me 4 potential points where we could have mins or maxes on the cage. And when I plug them in, I get 6 at 2 of them, and I get 0 at the other. And so what do you know? The ninja hound can transform into an eagle and escape at these 2 points. Right there. So, very exciting, yes? You guys don't partake in the ninja entertainment industry? No?
Are there any shows that are that precise?
I'm not sure this really would fit into the Naruto universe. But it seems plausible in the storyline of Naruto. I mean, there's a guy who has a monkey that transforms into a stick. Surely in a universe where a guy can transform into a stick, a dog could transform into an eagle. I mean, why not, right? Okay, enough about that. Problem 5, find the center of mass. So what's that mean? We got to find mass. And we got to find the integral, basically the weighted average over x, the weighted average of y. So the area, the mass I just get from integrating the density over the area, which gives me a third. The x center of mass is 1 over mass times the integral of x sigma dA, which in this case is x cubed, and that gives me 3/4. On the other hand, the y center of mass, integrate y times sigma, which in this case is x squared y, which ends up giving me a half. So the center of mass is at 3/4, comma 1/2. How many of you guys got that? I see somebody. Somebody else. Somebody. Okay, so at least some teams got that. That's good. By the way, so a lot of times, this problem, what if I had told you sigma of xy equals to x squared, great, but your region was this. What would you have done then to find the center of mass of that half circle? Yeah, I would hope that you would change the integrals we were just looking at into polar coordinates. I mean, x squared is not nice in polar coordinates, but the bounds are nice in polar coordinates. So, just a thought. So beware, we can mix and match ideas, right? I can combine a center of mass problem with a changing to polar coordinates problem, for example, right? In other words, polar coordinates is a tool in your toolbox. You should be ready to use it whenever you can. Now here, we cannot integrate this directly because we don't believe in power series, and we refuse to remember that there's a well-known Maclaurin series for that you could use. So since you don't believe in Maclaurin series, I say that you can't integrate it. I think I'm justified in my conviction that you guys don't believe in power series. Am I right? Yeah, okay. Maybe power series don't believe in you. Think about that. Like, power series in an inanimate object, I don't care. They can think what they will. Fine. Power series are good, though. You should think more about them. All right, I digress. So to flip the bounds, I need to draw this picture. So my original bounds say that what? They say y is between what? 2x and 2. And, oh man, I have not written stink. Well, it's in the picture, but I really should write down somewhere in here. I wish I had written somewhere down in here. The original bounds suggest what? 0 less than or equal to x less than or equal to 1 from the outer ones, right? And then 2x less than or equal to y less than or equal to 2. That's from the inner bound, right? Now that's also in my picture, right? So y is between the 2x and the 2. And x, of course, goes from 0 over to 1, which is where that and that meet at x equals to 1. Anyway, the type 2 characterization of this region would be 0 less than y less than 2, and 0 less than x less than y over 2. So with that change of bounds, all of a sudden, we first integrate over x, which is welcome news, because integral dx is just x, which gives us a y over 2, y squared dy. And then we're like, well, that's not a problem. This is just 1/2. This y e to the y squared is 1/2 e to the y squared. And so this is the antiderivative of that, which is easy to verify. And so there you go. Any questions? Comments? Oh, wait a minute, no, just questions. I'm not interested in comments. No. You guys look excited about this test tomorrow. Excited? No? It's too soon? Too soon. Let's see here. I don't know. When I gave this test, as I recall, students found so many ways to butcher this. Like, this should not be a difficult problem, but in practice it was very difficult because the students paid very marginal attention to the bounds. But the bounds are so very important. In other words, this x greater than or equal to 0 is not some like, I don't know what that means, I should just ignore that kind of thing. Like, I'm just gonna put 0 to 2 pi and hope it works out. No, you got to think through it. Most of them have graduated, so it's fine. This is from like 2014, I think. So, anyway, Anyway, x greater than or equal to 0 gives me this part of the disk. And then I would suggest that the radius is 3, right? 0 less than r squared less than 9, 0 less than r less than 3. And so that's minus pi over 2 down there. It's pi over 2 up here. So why not we use that range of angle would be the most convenient thing to do. So that's what I did. And then I just have to integrate, right? So I did that. This is r squared, right? dA is r d theta. And I think I chose to put the theta integral first because it's easy. And then the r integral, well, that's a u substitution, basically. Right? Any questions? All right. Careful with the bounds, guys. Careful with the bounds. Let B be part of the ball of radius r centered at the origin. What did I do? Oh, okay. So in the first octant, where x, y, and z are all non-negative, my density, mass per unit volume, be 1 over 1 plus rho squared for fun. That's the mass density of the ball. Calculate the mass. Aw, man, I didn't say calculate the center mass. That's no fun. Where is the center mass, though, guys? Can you tell me? It is at 0, 0, 0. Very good. Has to be, because the mass density is just a function of the radius. So everything else being equal, there's no preferred point on the ball except for the origin. So by symmetry alone, we can see the center of mass would be the origin. That's true. So that's why I didn't ask that. I just wanted to calculate the mass. So to calculate the mass, we integrate the mass density times dV, which in this case is that, because the spherical volume element, remember, is rho squared sine v d rho d phi d theta. And I also got to be careful, right? I'm interested in this 1/8. It's 1/8 of the whole sphere, right? And this is where both the phi and the theta range from 0 to pi over 2, right? And and this is nice. There's a rectangular bounds, the integrand factors into functions of rho, theta, and phi, respectively. So I can just multiply the respective integrals. That gives me pi over 2. This gives me 1, I think. Yeah, 1 pi over 2. And then this thing, right? So there is a reminder that you still need to know how to integrate things, and not knowing can hurt you. Some of you would be kind of, in trouble here. Now, don't despair. If this happens to you, if you can't do this, try to do everything else and do it well. And just explain in words, if I could do this integral, this would be what the answer would be, whatever that works out, 2 times that. And, and I'll maybe take off 5 of 20 or something, or 3 of 20. It depends on what else you did, but I do give partial credit, of course. But anyway, that does work out to r minus inverse tangent of r in that case, and so there's the answer. Actually, not that bad an integral when you just do the algebra. Here's the ellipsoid problem, which we worked in class the other day. Woohoo! And here's an example of what I was talking about. My solution, you notice, does not prove that this is 4th pi over 3. This is something we've done before, so it's a result that's well known, and you can reference that the volume of a unit sphere is 4 pi over 3. We fixed the 2 in class, thankfully. With that change, what was that noise? That was not my beep, was it? I heard a beep. Is the audio fine? Yeah. Okay. Anyway, so this is the inequalities. We have z ranging between that and that, y ranging between that and that, x ranging between that and that. And if you study these, they're exactly saying that you're in the first octant of this sphere of radius 2. So I can again do the angles ranging from 0 to pi over 2 and the radius ranging from 0 to 2. And there you go. Now, of course, I guess if you're a glutton for punishment, you could just try to do the Cartesian integral directly. And if you're really good at your trig substitution and are just a calculational beast, maybe you can make it through. I don't know. I don't recommend it. This is the last problem in the math battle. Here I started you with a diamond with those vertices, and I said change coordinates to calculate the integral. So this time I did not tell you what the new coordinates should be, right? So you had to invent. I'm going to make this be u. I'm going to make this be v. If you did the opposite, then you could still solve it, but it would reverse the meaning of u and v, whatever. So 2u is x plus y, 2v is y minus x. So I can add or subtract these to get y is equal to u plus v and x is equal to u minus v. I can take my xy point, map to my corresponding uv point, and it takes the unit, it takes the diamond and maps it to the unit square. It's not written in stone that the transform region has to be the unit square. It's just that every problem I've shown you this semester happened to be that. That is a coincidence of the semester. Maybe I should try to fix that on the test. Make sure I give you one where it doesn't transform to the unit square. No? I don't need to? But consistency is key. I don't want to give you the wrong idea, though. I mean, I'm afraid that if I give you yet another one that transforms to unit square, it's bad on my part. So I have to think about that personally. But go to unit cube. I was thinking about that. I'm missing that kind of problem in my repertoire. So I call it Nathaniel's unit cube problem. But I wouldn't call it the unit cube problem. I just call it Nathaniel's problem that everyone has to do. Let's see here. So are you armed?
Armed?
I mean, have you some kind of weaponry?
I'll keep some markers with me.
Oh, you see the markers? Okay. Anyway, so then once you make that change of variables, the integration becomes pretty cut and dried. Yeah. Remember, when we change variables, we have to do what? Change the integrand, change the bounds, and remember, we have to use the Jacobian to adjust the measure, right? So the dA in xy coordinates becomes the Jacobian times du dv, which in this case works out to 2 du dv, right? That Jacobian tells us how the area is getting rescaled under the transformation is what it means. So Anyway, what else do you guys want to talk about? We have a couple minutes. Anything in the missions? Yep.
Could you do a problem where you have to switch from dx dy to dy dx?
Sure. Let's see here. Suppose we have something like the integral from 3 to 5, the integral from, I don't know, 2x to x plus 10, right, of f of xy, dy dx. So suppose we're supposed to switch the bounds, right? So what I do when I'm faced with something like this is, first of all, I come to terms with what I'm looking at. I've got 3 less than or equal to x less than or equal to 5. I've got 2x is less than or equal to y is less than or equal to x plus 10, all right? Now, I may have to, we'll soon be the judge of whether or not my problem is reasonable. If needed, we'll adjust it to be reasonable. So at this point, I've got to draw the picture and find out. We'll soon find out if this is really what I wanted to do to us. So we're going from 1, 2, 3, 4. So here's my 3, here's my 5, roughly speaking. 2x. What's 2x do between 3 and 5? It starts at 6. 6 to 10. What's the other one do? So this is ranging from 6 to 10, and this one's doing what? 13 to what? 13 to 15? Ha! Hooray! Okay, so it worked. Although I may regret it. So, so here's the, oh no. Oh, this is so very horrible. Oh, this is awful. You see why this is awful? This is awful because if I change it to type 2, I have to do this part, right? I have to do this part. And then I still have the middle part, which is still different. This is like a really, really stupid choice on my part. Let me try something else. There's no chance for us in the time we have for that one. Let's try something else. What if I had the integral from, say, minus 1 to 1, the integral from 0 to the square root of 1 minus x squared, f of xy, dy dx. This one will work out better. So here, what this says is minus 1 less than or equal to x less than or equal to 1, and 0 less than or equal to y. So if I draw a picture of the region here, I mean, this is the integral over some region of f dA, right? My point is that this region is actually this half circle, right? So how would I recast? Now that I can recast as a type 2 region without so much trouble, right? Because if I think about a horizontal line here, there's a clearly defined right x and left x, and it's the same for the whole region. See, the drag with my previous example was that my left and my right is different in each one of the differently shaded regions, which makes it a really mean question if I say change it to a type 2 integral or integrals, because you have to break it up into 3 stupid pieces. Anyway, this, we have what? What's y going between? The top y is what? So in the type 2 description, I would say 0 less than or equal to y less than or equal to 1, right? And let's see here, the circle, x squared plus y squared equals to 1. So what does that tell me? X is equal to 1 minus y squared, x squared. So x is equal to plus or minus the square root of 1 minus y squared. So what I have is I have minus the square root of 1 minus y squared. less than or equal to x less than or equal to the square root of 1 plus y, 1 minus y squared. In other words, the integral over r of f dA can be rewritten as a type 2 integration of the following form: 0 to 1, and minus the square root of 1 minus y squared to the square root of 1 minus y squared of f dx. Find f of xy dx dy. And that actually would be a reasonable test question as it compared to my first one, which would just be mean. So I had to give my first version of my test this week to linear algebra. I told them that my first version I make of any test you don't want to take, because as I do revisions, it gets easier, right? So they had the misfortune of taking the first version this week because I ran out of time. Yes, sir.
Are we going to have any volume problems on our test?
It's possible. Sure, why not? I mean, I don't know. Is it possible you have a hypervolume problem? I mean, it's possible. I don't suppose it's likely, but it's possible. Actually, I think I know of a problem which is actually manageable, though.